Alright, welcome back to Geometry 2.4. We're going through this book, but you can learn the ideas even if you don't have the book, but you need the book if you are taking the class from me. So we're on page 96, Reasoning with Properties from Algebra. So where we're going is to learn how to write proofs in algebra, in geometry and algebra, anything, any kind of math, and it's sort of like our papers, writing these proofs, and it's kind of like being a lawyer, and it's kind of like haiku poetry. There's just a certain way you do it. So we're going to do it, and I've had certain students who think it's fun, so maybe you are going to be one of those who think it's fun. Alright, so first, we talked about last time about deductive reasoning and how you use postulates, laws, definitions to reason, and that's what we're going to do. And these are properties that we can use in our proofs to reason with. So one is the addition property, and that's in algebra. You're allowed to do anything you want in an equation as long as you do it to both sides, including adding the same thing to both sides, or subtracting the same thing, or multiplying the same thing, or dividing the same thing. Hold on, I forgot to hit my timer so I don't go over. You can do anything you want as long as you do it to both sides of the equal. Now, last tape I told you about the law of syllogism and about how it was going to have, it's important, but it's going to have a different name later in geometry. Well, later is today. And this is what it is. Well, we're not going to do that yet, sorry. And there's actually going to be three things that are really important, and each of these are going to have, they're so important, they're going to have a hand sign to go with them. It's going to help you remember. I've had kids come to me years later and go, "Miss Blackburn, I still remember." So you will too. Alright, so the first one is the reflexive property, and the symbol for it is this. This is a mirror I'm holding up to you, and who do you see in it? You see yourself. You see your reflection. So in geometry, we have a lot of things that you're going to think, no duh. Well, but you have to do it. You have to state things that seem so obvious. And one of the things is that something is equal to itself. U equal U and A equals A. It's called the reflexive property. You're seeing your reflection in the mirror I'm holding up. The next one is the symmetric property, and it's if A equals B, then B equals A. It's that you can flip it. Your hands are symmetric. Pinky, they're not the same. You can't put them right on top of each other, but they are mirror images of each other, just like how those equations are mirror images of each other. So this is the symbol for the symmetric property. It's like a butterfly. Butterfly wings are the same way. Your hands are this. So if I hold my hands up like this, it means that the reason why we are allowed to write this down is the symmetric property. And I always think of it looks like a butterfly, and then I think of Napoleon Dynamite doing the Happy Hands Club. Alright, next one is the transitive property. This is the law of syllogism. If A equals B and B equals C, then A equals C. The transitive property is what it's called from now on. And the substitution property is if A equals B, then B can be substituted for A. So the substitution property is you're allowed to substitute things. Now, a lot of times when we substitute, we have to sing a song. It goes, substitute. It's by the Who, it's before my time, it's before your time. But songs help remind you what to do next. And I know I can't sing, so you don't have to tell me in the comments, I already know. But it adds to the comedic value, so there you go, it's all good. Okay, so I'm going to show you how to write a proof using something you're familiar with, an algebra problem. And so if this is a proof, everything I do, I have to give, it's called a statement, and I have to give a reason why I wrote it. Now the first thing you do when you do an algebra problem is you write the problem down. Why are you allowed to write the problem down? Because it's given. So the first step in any proof is you write down what is given. So you should never leave a proof blank. because you can always write the given and get some points. It's not all or none. None, you can get some. Okay, so if I was doing this algebra problem, the first thing I want to do is to combine those x's, so x is all by itself. So I would want to move 3x over to 5x because 3x is smaller. And how I move things in algebra is by doing the opposite. This is a positive 3x, so I do negative 3x or minus 3x from both sides because I'm allowed to do anything I want as long as I do it to both sides of the equals. 3x minus 3x is 0, but I don't write 0, that just confuses things, I cross it out. And 5x minus 3x is 2x. And I bring down everything I didn't mess with. Now, why am I allowed to do this? Because of the subtraction property of equality, or the subtraction property. Okay, so now, how do you solve for x? Well, you ask yourself, why is x not alone? Why is it not alone on this side of the equals? Well, there's two things. It's being multiplied by 2, and it has a minus 18. Whenever you are doing algebra, you work from what's further away from the x to what's closer, and by doing the opposite. And the opposite of minus 18 is plus 18. And what I do to one side, I have to do to the other. Those cancel out. I bring down what I didn't mess with. 18 plus 2 is 20. Why am I allowed to write this down? Because I added to both sides. It's the addition property of equality. Okay, now, why is x not alone? It's being multiplied by 2. So the opposite is divide by 2. What you do to one side, you do to the other. And 20 divided by 2 is 10. Why am I allowed to write that down? The division property of equality. All right, that's a proof. Normally we would number it, like this would be 1, and then our next one is 2, 3, 4, but I didn't put numbers on it because this is algebra and that would confuse things. What we normally do proofs with is things with lines and shapes, but I'm just showing you with things you're familiar with algebra. Let's do the next one, okay? Why is this allowed to be written down? Given. I have to stick it over here because I didn't leave enough room there. Okay, now what do you do first in this problem? We get rid of what's ugly, and what's ugly are those parentheses. So I draw arrows to remind me to do the distributive property. I always draw the arrows because I'm dyslexic, and anything that I can do to help organize helps me overcome that and succeed. So I bring down what I don't mess with. Now negative 3 times negative 9 is negative 27x. And negative 3 times 12, oops, it's not positive. Whoop, whoop, whoop. Negative 3 times 12 is negative 36. And now equals negative 64. Why was I allowed to do that? The distributive property. Okay, next thing I would do is gather up my terms. Now, gathering up terms, if you have x's on the same side of the equal, you have to get them together. And this activity has a song and a dance. It goes like this. Gathering up your terms, it's 2 on each side. Stowing away the time, 2 on each side. Gathering up your terms. Okay, if you're not singing and dancing when you do math, you're not having as much fun as you could have. Alright, so these are my terms that are being gathered up. 55 x minus 27x, I think that's negative 28x. Let me double check so I can cheat and not have to do the math. Yes. Now if you're following along in your book, I changed the z's to x's because I'm dyslexic and z's are too much like 2's. So, y'all think I'm crazy. If you're not dyslexic, you can understand. Okay, so why is it allowed to do this? If you gather up terms, you don't write gathering up terms, you write simplify. S-I-M-P we'll do for our abbreviation. We're going to simplify. I got my minus 36. Okay, now, why is x not alone? It's got a 28 and a 36. We work from the outside in. The opposite of minus 36 is plus 36. What we do to one side, we do to the other. Those cancel out. We bring down what we didn't mess with. and this equals negative 28. Why are we allowed to do this? The addition property of equality, because we added something to both sides. Now, why is x not alone? It's being multiplied by 28. What's the opposite? Divided by 28, what we do to one side, we do to the other. So x equals negative 1. Why are we allowed to write it? The division property of equality. Ta-da! That's a proof. We just proved that this is true, that x equals negative 1. And we did it using the rules of writing a proof. Now let's do one that's more like what you would really do in geometry. Okay, we are given that line segment AB equals line segment CD, and we're asked to prove line segment AC equals BD. What you prove always goes on the bottom line. So, why were we allowed to write this down? It was given. So even if you don't know how to do a proof, you can write that amount down. All right, now, so what we're going to do next is we're going to say that AB plus BC equals AC, and we're going to say that CD plus BC equals BD. And the reason why we did both of those is the segment addition postulate. Remember, we learned a long time ago that you're allowed to add segments if they're next to each other. So the next thing we can say is that, let me say something real quick here, that the proof in the book is in a slightly different order. It doesn't matter. There's more than one way to be right. There's lots of ways to be wrong. Okay, so the other thing that I need to say is that these two things equal each other. Segment AB plus BC equals CD plus BC. And this is the same thing as that, except we've added BC to both sides. And the reason why we're allowed to do that is the addition property. You're allowed to do anything you want as long as you do it to both sides of the equals. And now that we have said that that equals AC and that equals BD, and that these things equal to each other, then we can say that these two things are equal by substitution. The substitution property, which is that one right there. Now, this is probably a little hard for you, but the more you practice, the better it'll be. The last thing that's in the book is there is a proof that they do with the Talladega. I looked up to see what it looked like. The Talladega racetrack in Alabama, and how they prove that certain angles, certain banked curves on that racetrack are the same. I want you just to look at that if you are following along in the book. I don't expect you to be able to do that yet. We're a little ways away from that. But just to sort of see if you can understand how they proved which of the angles were the same at the Talladega speed racetrack in Alabama. I've seen it. I didn't go to a race, but I drove by it, and it's much bigger in real life than it looks on TV. Math is fun.